Greetings. Welcome to a brief discussion about Wi-Fi Enhanced Open. The target audience for this discussion consists of those with a modest understanding of the 802.11 protocols. It is also hoped that the layperson will find value in this discussion. Let's begin. The Wi-Fi Alliance is a nonprofit organization that is concerned with the advancement of Wi-Fi technologies. The organization certifies that the technologies are interoperable in terms of certain standards. As seen in the below images, the Wi-Fi Alliance has a scope that spans many categories. Some of the foundational certifications from the Wi-Fi Alliance include WPA, which is somewhat gone to the mode of legacy in terms of security. And WPA2 is currently the staple security protocol. WPA3 was just released in 2018. Enhanced Open and Easy Connect are complementary protocols to WPA3, so they're new as well. Let's take a closer look at WPA. There are common components, in specific two common components in regards to WPA, WPA2, and WPA3. Those components are authentication and confidentiality. And it's important to note in terms of Wi-Fi authentication, there is a focus on ensuring that authorized users are permitted access to the Wi-Fi network. Unauthorized users are denied access. And confidentiality is pretty much what it means, keeping the modes of communication secure. And confidentiality is achieved by primarily two means within the 802.11 WPA, WPA2, WPA3 domains. And those two methods are WPA personal, which is linked to a pre-shared key, a key that's shared among all the participants, and something known as WPA Enterprise, which requires a third-party authentication service. So the WPA personal uses the pre-shared key as a control to produce authentication as well as the confidentiality encryption keys. The WPA Enterprise, we're going to lean on a third-party server. You have to specify the IP address of the server, the port that the server is going to be used to communicate, as well as a shared key that's used for authentication between the access point and the server. There are some pros and cons. First, the major pro with all the flavors of WPA is that you have authentication and confidentiality. The major con to the personal mode is the pre-shared key, which means that although you have a measure of confidentiality, every participant has access to the pre-shared key, which means that there is a chance for one or some of the participants to capture traffic from all other participants, which may not necessarily be a good thing. And the major con in terms of the enterprise mode is the requirement of the third-party authentication server. It's not necessarily a complex setup for those in the enterprise setting, but it is somewhat of a complex setup for those who want to induce customers to participate in their particular venue, whether the venue is a coffee shop, a conference hall, etc. And it can be somewhat complex to manage. To address the needs of networking environments that consist of open spaces such as coffee shops, airports, conference halls. The Wi-Fi Alliance released Enhanced Open. The major bang with Wi-Fi Enhanced Open is that each individual unicast stream between the client and the access point has a unique pairwise master key that is used for encrypting the traffic between the individual client and the access point. So yes, there could be 200 clients associated to an extended basic service set, and each of the 200 clients will have an individually encrypted session between itself and its associated access point. And the great thing about this is that this all takes place without the use of a password. And Wi-Fi Enhanced Open also requires the use of protected management frames. So outside of the normal data traffic that's being transmitted between the clients, there's also some management or overhead type traffic that exists within the Wi-Fi domain. That traffic is protected. A key beneficiary of protected management frames is that legitimate clients can't be maliciously disassociated from the Wi-Fi network, which in essence will be a denial of service attack. Wi-Fi Enhanced Open is based on the Opportunistic Wireless Encryption standard, which is specified in RFC 8110. It requires Diffie-Hellman process to generate a pairwise master key between the client and the access point, which can then be used in a four-way handshake to create session or traffic keys for the data traffic. As mentioned earlier, OWE has some major benefits, and they are encryption of individual streams between clients and access points, and that takes place without the use of a password or any type of pre-shared key, which makes it a very easy process for end users. However, there are some concerns. The Diffie-Hellman process is unauthenticated. There is no authentication within Enhanced Open, which means that there's no way to verify what devices are connecting and what they are connecting to, which sets up a perfect breeding ground for a man-in-the-middle attack. So there's nothing to stop someone from introducing a rogue access point that is broadcasting the same SSID as a valid access point. So this means that legitimate clients can associate with rogue access points, and the session between the client and the access point will be encrypted. However, the rogue access point can then run that data from itself to a legitimate access point or the legitimate wireless distribution system. But the link between the rogue access point and the legitimate wireless distribution center can be analyzed, and the traffic in essence will be in plain text at that point. Hence, users will still have to exercise an extreme amount of caution when accessing a wireless distribution system that's outside of the user's control. I recommend that any sign of suspicion should be cause for the user to not associate with the respective access point. OWE is designed to replace open networks, which I'll term as legacy open, which means those networks that do not require any type of authentication. So to the typical user, OWE will look no different than the legacy open network as seen in this example. We have an SSID that's notated with OWE to indicate that it's an OWE network. But notice that there is no padlock associated with the network, just as the case with the legacy open network, the Aruba visitor network. Let's take a look at how clients join an open network. That could be a probe request and then a probe response. And then there's the open authentication request, which in essence, the client say, hey, I want to be authenticated, so let me in. And then the access point say, okay, I'm going to let you in, you're in. And then there's the association request, the association response from the access point. Then the client is associated with the access point, and the traffic is in plain text. Think about that in comparison to OWE. We could have a probe request, then we'd have a probe response, then we have an associated request. Notice that the Diffie-Hellman component is added to the association request as well as the association response. We produce the pairwise master key, go through the four-way handshake, then we get the traffic encryption key. And from that point on, the traffic is encrypted. Again, this is without establishing a pre-shared key between the client and the access point before this process occurs. To facilitate a smooth transition to OWE, there is a transition mode that is backwards compatible to the legacy open networks. Basically requires the administrator to configure a single SSID. The AP will automatically produce two BSSIDs with separate beacons. The first SSID will be for the non-OWE clients, and the second SSID will be there, but it will be hidden. The 802.11 frame has multiple fields known as information elements. There's going to be an information element in the transition mode frame that will serve as an indicator to OWE clients that see the legacy open network to be aware that there is OWE support, and then those OWE supported clients will transition to be associated with the OWE hidden SSID. Another benefit of the transition mode is bridging, so that the broadcast and multicast traffic will be bridged between the non-OWE SSID as well as the OWE SSID. So as I conclude this presentation, I want to share with you some considerations. OWE does support PMK caching, which simply means that if a client and access point were engaged in communication earlier in the day, and then the client attempts to reassociate with the access point later in the day, they do not have to go through the Diffie-Hellman process. They can use the cache. They can use the cache pairwise master keys. Also, OWE is a replacement for the open network. So users should not expect to see that padlock when locating available Wi-Fi networks. Also, there is no end-to-end encryption. There is only encryption between the client and the access point. Once the traffic leaves the access point, the traffic could be in clear text. Also, there is no protection against active attacks such as man-in-the-middle or rogue APs. If there is a requirement to use authentication or higher level of security, one should not use OWE as a substitute for WPA2 or WPA3. Earlier, I mentioned that there is no authentication within OWE, so therefore it's going to be quite difficult to implement any type of accounting. However, you can deploy captive portals within an OWE environment. What will happen is that the client and access point will complete the OWE process. Then the client will be automatically directed to the captive portal. And from that point, the captive portal can demand that the client watch a particular video, click on some type of agreement, or perhaps insert credit card information. At some point, the captive portal will have the responsibility of making the decision as to whether or not to allow the client access to the network. But again, the captive portal kicks in after the OWE process has completed. Okay, this concludes today's session. I hope to see you in cyberspace in the near future.